Okay, so let's get started. So this is the second session. I always struggle between how deep to get into packet analysis and how much I shouldn't. So I constantly need that feedback, and I think next year or the next session I may just do purely introductory. So let me ask you guys a question. Be honest. How many of you consider yourself more on the novice side of doing packet analysis? Just show of hands. Okay. How many of you are on the hardcore, there's nothing I can't solve with Wireshark side of the house? A couple people, okay. Don't be shy. Okay, all right. So given that, it might make sense for me to do more introductory stuff than hardcore stuff, but then hardcore stuff is kind of fun too, right? So maybe I'll split this into not continuation of different use cases, but one hard, one, I don't know. So give me that feedback, please. Okay, that's all I'm asking. It's in the app. Give us feedback of examples and how in-depth I should get. So again, my name is Han Sang Bae, for those of you that joined for the first time. I don't have a slide presentation, so I should do this again. For those of you that need to get a hold of me, okay. And you can Google it. You can Google my YouTube page, and you'll see a bunch of Sharkfest sessions, and you'll see other webinars, how to set up Wireshark, how to set up the columns, best practices, etc. Okay, and I'm sure you can Google stalk me and get the information on everything else. So that's all you, pretty much. I'm supposed to have a template, and I'm glad Janice is not in the room because she gave me a nice PowerPoint template that I forgot to do. All right, so we're going to continue from the last session, but these are all new topics. The philosophy is going to be the same. I'm going to show you some trace files. I'm going to show you how I solved it, but more importantly, you need to start thinking about what the hell would I do, right? So there's one thing I learned way back in calculus, and that's going back 30 years. And that's when the professor was up there doing examples of whatever he was doing, Diffie Q, whatever it was. I sit there and nod and like, yeah, this is easy. I got it, transform, integrate, got it, plus a constant, got it. And then I go home to do my homework. I'm like, what the hell? Like what the hell did he do here? And then the most annoying thing was, textbook that says, it can be easily shown that, boom, it's like, no, it's not easy at all. Or I leave it up to the audience or leave it up to the reader to take it to the next step. And then you go and buy like Howard Anton, that's the author's name, I still remember it, supplementary textbook to, but at the same time, when I'm presenting up here, because I am recording this, you don't really have to take as much in detail notes, right? You can write down like interesting tidbit of what I said, but it's better if you listen and absorb as much as you can because it's being recorded. I'll double check. It is being recorded, and I'm going to set the record by uploading to YouTube tomorrow at the latest. Now I'm hedging already. So you'll have that. You'll have, you can go back in time and say, what the hell was he talking about? So by all means, please, try to absorb as much as what I'm saying because I go into the philosophy, the backdrop of troubleshooting more so than the pure mechanical use of Wireshark, okay? Because you don't need me to teach you the mechanical part. You have your methodology, I have mine, but it's more important about, I guess the best way to think about it is come into my brain as I look at a trace file, and you'll see what direction I'm taking. Make sense? Don't forget to ask questions, and again, throw things at me if I don't repeat the question for the YouTube audience. All right. So the first thing I'm going to show you is an example of sometimes you don't get a perfect trace file and you're expected to solve things, okay? This happens a lot when you use SaaS because you can't get a two-sided packet capture because it's internet, right? Guess what, folks? You use SaaS, internet's your backbone. Think about that. The other thing is you can ask, but they're not going to do a packet capture for you unless you happen to be a really ginormous customer of theirs, and then they will bend over backwards sometimes to provide you with additional information that they may not. The problem is not all of you work for a 300,000 person company, right? So you don't have that ginormous 800-pound gorilla to force something from SaaS vendor. Or sometimes people on your staff or your employees make a mistake and put the wrong filter. Okay? And this was a case of that, where there's a physical problem with the capture because they thought they were capturing transmit and receive on the tap, and something happened to one, and so I got just the transmit. So this is actually a complaint of a SaaS service, and the business came and said, our network sucks because I can't upload these things up to the SaaS provider in time, and there's a big backlog, and it's all your fault. Probably heard that before, I'm assuming. So I said, well, hey, it's the internet, so you can always cop out by saying it's the internet, what are you going to do? But it turns out internet's pretty damn robust. So the days of being able to use the internet as your excuse point, that ship has sailed. All right. So what else could you do? Well, the only thing you can do is prove yourself innocent. I hate to use that, the mean time to innocence, but sometimes you don't have any other recourse because it's a SaaS service, and as long as you can prove from the point of entry, which is the laptop, to the boundary of your network, you're okay, then that's all you can do, right? Everything else is on either the internet or the SaaS provider, okay? So this goes back to my saying. Packet analysis is about getting a murder conviction without a body. I use this phrase all the time because it's 100% apropos. Okay? You need to get a murder conviction without a body, and that all the defense lawyer has to do to reasonable doubt is, he went to Costa Rica. Prove to me that he didn't go to Costa Rica. And then you have reasonable doubt. That's why it's hard to get a murder conviction without a body. So we need to build up circumstantial evidence. That's what we're going to do in this case. So again, this is a SaaS service. It's one-way packet. This is not a display filter problem. This is a packet capture of one side only. Okay? So, because TCP is two-way conversation, sometimes you don't need to see the other conversation to derive information. And that's what we're going to do. We're going to look for patterns, and we're going to say, what can we do using a simplex or one-way conversation. So methodology is different, but again, I'm a creature of habit, so I'll scroll down, look for things. And it's a very short trace file, nothing interesting to look at, except that 54-second delay. That's humongous, right? The other thing that I do is TCP analysis.flags, but it's completely and utterly useless because TCP analysis.flags requires two-sided conversation for the most part to work, okay? Unless what? Unless you happen to have captured the packet loss. In other words, and I said this in my previous session, but I'll repeat it because this is a new session and you may not have been watching the other YouTube video. When you're the sender, right, and remember where I'm capturing this from. I'm capturing this at the boundary of my network. I'm not capturing this at the workstation or the server. I'm capturing at the boundary of my network before it jumps into the internet. Okay? Make sense? So, if I drop packets in my network, what would it look like at the boundary of my network? Meaning, if I capture at the server, I know I sent it, there's no packet loss. Right? Because I'm the server, I sent it, I captured it, I know I sent it. There's no packet loss. But I'm capturing it at the boundary of my network. So the first thing I notice is, because I'm at the boundary of my network, if some packets got dropped between the server and the network, and for all you firewall guys, this is past their firewall, so it's not the firewall dropping packets. Okay? So I know that this is as far that I can see inside my network. The next hop is the internet, and I didn't drop a packet. So at least I got that going for me, right? All right. So, it's the circumstantial evidence number one. I didn't drop any packets in my network. Okay? However, if there were packet loss, outside of, I already proved my network innocent, but if the internet dropped it or the SaaS provider dropped it, what would I see here? I would still see retransmissions. I'm not going to see the triple dupes. I'm not going to see the acknowledgments coming back, but I can even actually go a step further. I can even say this was a fast retransmission, right? Because there was no delay in retransmitting that. If there was a long timeout, retransmission timeout, I can say this is a timeout, retransmission timeout, not a fast retransmission. There are reasons why you get fast retransmissions and sometimes why you don't get a fast retransmission, okay? But let me actually clear that point up since the difference between a fast retransmission and retransmission is what? Anybody know? What's the simple definition of the difference between a fast retransmission and a retransmission timeout? Not the effects of it, which is, collapsing the congestion window and dropping all slow starting, not that. What's the difference at the simplest level as a troubleshooter, as you're thinking about this? What is the difference between a fast retransmission and a retransmission timeout? Delay? Delay. So so I see what you mean about delay, meaning delay, I didn't get the feedback in time, right? And so you do a retransmission timeout. So you're on the right footing there, but I want even a simpler answer. Trailing packets. Is that what you said, Kinson? So trailing packets. So this is important. If you don't have trailing packets, you can't induce duplicate acts, okay? Triple duplicate, which is actually 4, kind of annoying, but triple duplicate means I have a packet train. Imagine a packet train leaving the station with 10 packets. And packet number 2 goes missing. Okay, so visualize that. It's very easy to visualize, right? Especially if you live in New York area, you're on the Metro North. They go missing trains all the time. So, yeah, I'll have to clean that up because I don't want to get sued by the MTA, but or liable or whatever. So the idea is, imagine 10 trains leaving the station. Train number 2 goes missing, but train number 3, 4, 5 show up. Then I can say, dupe back please, because I'm missing 2. Train number 4 shows up, dupe back, train 2 is missing. Next one shows up, train is missing, dupe back again. Dupe back, triple duplicate, the guy immediately sends. Imagine if the 10th train got lost. You don't have a feedback mechanism. TCP is positive acknowledgement. I need more trailing packets to force me to say, I'm missing packet number 10. But I can't because there's no 11, 12, and 13 coming into the station as the receiver. So sometimes this is bad. And I actually spent there a couple years back a packet trace file where that was occurring. Okay, and I spent, I think, 50 minutes on that one trace file because it was so interesting, the interaction, because, and this is, again, Cowboys and Indians movie, they always tell you pick off the last guy in the patrol and no one knows, right? And it's true. TCP suffers the same symptom. But this is not that, right? So because I can see a bunch of packets going out, and if a packet goes missing, I know that I'm going to see some duplicate acts, okay? And this is why I say I can tell if this is a fast retransmission or regular retransmission, because I will see dupe back, dupe back, dupe back, dupe back, and then I'll say fast retransmission. Even though I don't see that, if the retransmission goes out quickly, I know that's at a minimum of 1 round trip, because it takes a round trip for the acts to come back. I know that was a fast retransmission, okay? If the retransmission takes 200 milliseconds, chances are it's retransmission timeout. And then, of course, since I'm the transmitter, I will see the slow start behavior. This is how you can tell that there was a fast retransmission or retransmission timeout. Make sense? All right, so let's go to this trace file. Again, no packet loss. The delta is, again, sort of kind of interesting, right? These 12-second delays annoy me because I see 2 of them. So that's like consistent. I don't like, it's good and bad. You'll see that here's another one that's almost 12 seconds. So just by those 3, and here's another one, 12.5 seconds. Here's one that's 6 and 4 seconds. So this one's a little bit off, but I do see some cases where there's exactly 12 to 13 second delay. When I see a bunch of those, and I truncated this because you don't have to go through 5,000 packets. that tells me that it's more likely than not an application level delay, because there's nothing in the network A that holds on to things for 12 seconds, and B, it's never that programmatic, okay? So when you see repeated behavior, applications tend to cause that, not networks, okay? Because our packet processing time is phenomenally fast, and all we do is take it from one interface to the next interface. There's not a whole lot of things that can delay packets. Even proxies and firewalls, delays can be measured in the order of single-digit milliseconds, if that. Modern firewalls, almost nothing, okay? Proxies, IPS, IDS, maybe a little more, but again, not 12 seconds, okay? All right. So SYN, again, you're kind of limited here because, let me just make sure I'm recording. Yeah, I am recording. Because I can see that I have a maximum segment size, I have SAC, I'm doing timestamping, I'm doing window scaling. So a modern stack. I'm doing all the stuff that I should be doing. I don't know what the other guy is doing, all right, but, okay. So I see that obviously this is SSL, so there's client hello, there's gonna be server hello, we're gonna look at the different cipher methods and agree on one and move on after this encryption, all right? And then, so this is nothing interesting, so these are just setup of, the setup of SSL, et cetera. So it's not the application yet, okay? All right, so then we come to here where I send 326 bytes of data, and I see an acknowledgement here. So let's come back to here. And what's his acknowledgement number? 3407. So let me see here. Hold on a second. So I'm at the Sharkfest. Okay. And the feedback, the only way that I know that, because I can't see the other sequence number, is for me to look at the acknowledgement numbers incrementing. Okay? Because what happens when you send me stuff, I acknowledge by sending you increasing acknowledgement number, right? Because that's how it works. So when I look at the acknowledgement number here, all right, so let's look at the acknowledgement number here. I know that this is increasing, so the other guy sent me stuff, but I'm doing client hello and server hellos. So I don't expect this number to be very big, and it's not. The difference between 3348, 2734, not that big, okay? So if we come down to here, where we think some application level transfer is going on, it could be here, for example, right? So there was a delay of me sending some acknowledgement back, and acknowledgement number is same as previous packets, so between here and here, the SaaS provider didn't send me anything because my acknowledgement number didn't increase. But it did increase, so I sent it some data, right? 1368, 669. Again, what do we talk about the buffer tearing thing? It looks like it's sending, trying to, instead of sending full packets, it may not, or it could be just the application set to 2048, 4096, who knows? So looks like there might be some buffer tearing going on. So what's the difference between 2097 and 2301? So let's do that math. 2970, ACK number, 2301 is 669 bytes. So the other guy sent me 669 bytes worth of data. Is that meaningful? Not really. What the hell do I know about this application? Okay, right? But I filed that away. I keep looking because I don't have much of an option here. This is a single-sided TCP trace. I'm working with what's given to me. So let's look at the next one where it jumps up. So interesting thing here is that there is a delay, I'm the 192.168.1.1. Even though there was nothing between here and here, the acknowledgement number did not increase. Acknowledgement number did not increase, and yet there was a 60 millisecond delay, and I'm sending data. So chances are this is me, my server, thinking about something and then sending it out. That make sense? So does that make sense? Yeah? So again, I'll repeat that one more time. The acknowledgement number didn't increase between packet number 13 and 14, yet there was a 60 milliseconds of delay. And so there was nothing the SaaS provider was sending to me, and so this delay is on my server, okay? He was thinking about it, wrapping it up, doing a database query, who knows? And he sends packets. He sends 53 bytes, which is interesting in and of itself, and then there's a full-size packet, and then a small packet. So what's the difference between here and here? Because there's yet another delay where I waited for the ACKs to come in probably. I'm pretty sure I'm gonna have a delayed ACK issue here because there was an odd number of packets that were sent. So what's the delay between here and here? Let's take a look. 6269, 5352, 917 bytes. Previously it was like 660 something, right? This is 917 bytes. Again, what the hell do I know? This could be application level acknowledgement. This could be the SaaS provider saying, give me the next chunk, or here's an answer to your question. You asked for this, I gave you that. Don't know. All right, so let's jump down to the next. So I was at what, packet 18? So let's go back to where we jump again. So let's look at this guy. So this is 7451. I'm sorry, yeah, 7361, 7361, 7361. So this is me sending a bunch of data, and here's 8278, acknowledgement number. I'll put it right next to it so you don't get confused. 8278, 7361. Huh, 917 bytes, just like the previous. So what do I know so far in the two instances? I sent a bunch, so remember, keep that framing of reference in your mind as you're slicing and dicing packets. I sent some data, I waited a little bit, I sent some more data, I waited a little bit, I sent some more data, and every time in between, there's 917 bytes of data coming back from the other application. Okay? Let's see if this continues. So, excuse me, if we look at this guy, 10223, 9306, 917 bytes, again. So we now have 3 or 4 or 5, I can keep doing this, instances of me, the server, thinking about something, sending the data, the SaaS provider thinks about something and gives me back 917 bytes, like clockwork. Who does that? What kind of application does that? And this, again, comes from experience. And if you think about it, this is a conversation, right? This is a TCP conversation. This is a sender and receiver, client and server, my server, SaaS server, talking, having a conversation. And what kind of conversation always ends up with 917 words, 917 bytes of data? I'm just asking generically, right? It's not a trick question. What kind of conversation in your day-to-day life?
That would be canned response.
Canned response. You're asking or getting an answer about the same thing over and over. And I just realized I probably blew out the eardrums again. I was excited. Canned response. In other words, you're asking the same question or you're getting the same answer, depending on whether you're a database or updating a database. For example, may I have the next 20 rows? May I have the next 20 rows? Some data comes back. Each row has different variable length. It could be 1,000 bytes, 100,000 bytes, 10,000 bytes, depending on what row you're asking. But your question to the database server is always, may I have the next 10 rows? 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 This is a very symptomatic of a database update, and database telling you, I got it, give me the next. I got it, give me the next. I got it, give me the next. Okay? So I asked the SaaS vendor, I said, clearly there's a database at play here. They say, yes, there is. I said, okay. So again, I'm trying to get a murder conviction without a body, because the SaaS provider can always say, it's you, not me, it's the internet, what are you gonna do? So I've proven that I don't have packet loss up to my network boundary. I know that for a fact. Beyond a shadow of a doubt, there's no packet loss. Even on the internet, I know there's no packet loss. Because if there were packet loss, right, because they immediately jump to, well, it's a one-sided trace, you can't be sure. I said, yeah, I can be sure. Because if I sent you stuff, two things are gonna happen. Either there's more packets that generates dupbacks, or there's a timeout and you're going to retransmit, or I'm going to retransmit. And that retransmission timeout is 200 milliseconds, guaranteed. Make sense? Because remember, if I sent you and I happen to lose the last packet of that packet train, I'm going to have a timeout and I am going to retransmit. If a packet in the middle got lost, I'm going to get dupbacks. So I know for a fact that the SaaS provider got this data without missing a beat, without a packet loss. And I asked him, you're a database? Yes, we're a database. And I said, okay, riddle me this. I see varying levels of delay between this pattern of 917 bytes, me sending you something, 917 bytes, me sending you something. 6 seconds, 8 seconds, and then there's 12 seconds of delay. I see this more often than not. I said, okay, why is that interesting? I said, well, because you have a database, you have a DBA, can you run some traces for me? Can you look for transactions that take 12 point, subtract the round trip time, et cetera, flight time, et cetera? And can you see in your log if there's a slowness, a query that takes on or about 12 seconds? Because I see that repeating. Sometimes it's 7 seconds, sometimes it's 3 seconds, sometimes it's 8 seconds. And they said, well, you're a big gorilla, maybe we can do that for you. And I said, well, you kind of have to, because this is looking like it's you guys. Right? All evidence so far points to you. It's not packet loss, you can't blame the internet. So whatever slowness is occurring on your prem. I've proven that. Beyond the shadow of a doubt, I've proven that. So I got the DBA involved, I asked him to look at the logs, and then lo and behold, they're doing what? With a database, when you get data, what do? You commit, you truncate the log, right? You commit it to disk. And that process was taking, because it was under duress, it was taking anywhere from 7 to 12 seconds. Okay? And the DBA went, well, that's not right. And I was like, yeah, exactly. Thank you, click. Okay? So this is an example of how when you're given a set of packets that are not 100%, you can still distill a lot of information out. Okay? Does that make sense? And this is nothing more than me walking through my usual workflow, and when I'm limited by what I can see because the data given, I try to discern as much information I can. Did I know that I was going to find this pattern? Hell no, I didn't know. I expected random bytes coming back to me, okay? And that would have been that. But as soon as I saw repeated same number of characters coming back, I knew it was a database application, because databases do this all day, every day. You don't believe me? Do a packet capture of any database application. You're going to see one of two things. You're going to see prefetch size at work, okay? Prefetch is a database concept of, if you ask me something, I will give you X number of rows of data. Default can be 10, it can be 100. For modern database servers, set up a prefetch size of 50,000. Then it'll go fetch 50,000 rows of data and stream that data to you. And what do you think is going to happen at the very last packet? What are you going to see when you're seeing a stream of data with 50,000 rows of database rows coming? What do you think you're going to see at the very end of that trailer? A smaller than full MSS, probably, and a push bit, the buffer tearing that I talked about. And then what are you going to see? More importantly, what are you going to see? So I'm the guy doing a select query, and I asked, a database, give me everybody whose last name starts with B. And oh, by the way, give me 50 rows at a time, please. So everybody's last name is different. Mine is short, yours could be longer. So I'm going to see some varying amounts of data coming back with a push bit. That's the, hey, here's the last packet, I'm flushing the buffer, slap a push bit on it, and off it goes. It's a sign to look for. The second thing you want to look for is your response that doesn't change. Why? Because what you're saying to the database is, May I have the next? May I have another? May I have another? May I have another? May I have another? Okay? So this is like the Niedermeyer action from those of you that recognize that reference. Okay, thank you, sir, may I have another? Thank you, sir, may I have another? Make sense? So put that into your library of things to look for. When you see repeated number of bytes coming or going, that's somebody asking the same questions or someone giving you the permission to move forward. When you're uploading data, you're doing an update query, the database might say, go with the next, go with the next, go with the next, give me the next chunk, give me the next chunk, give me the chunk. So again, most database, don't believe me, give it a shot, okay? And there are different ways to improve that by modifying the ODBC, JDBC buffer sizes. If you're still using ODBC, in control panel, there's an ODBC application buffer size. It's tunable, you can make that bigger. That's the prefetch size. JDBC, there's a JDBC connector string. Oracle, there's a SQLnet that says, I like my prefetch size to be 1,000, 50,000, 100,000, okay? I've shown in the past the difference of prefetch size. Actually, I showed it earlier. I'll just show it to you for completeness sake because it was last year that I showed some of it. So this is a bad database. Right? What do you notice immediately as I scroll by? That's 17, right? Okay, and yeah, it's, this is the extreme case. 100.100 server, this is the client, so the client says, may I have the next please? And that happens to be 17 bytes. And the database says, here you go, here's a row of data, we're 363. May I have the next? Here's another row, 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 okay? So this is the database. Again, you're paying a round trip penalty because every time you have to ask for the next row to come to it. So this took 3 days before they quit because they moved it from New York to New York to New York to Dallas. And that's why you have 40 milliseconds of round trip delay. That's another thing for you network guys. You have to know your latency in your network. You have to know it like that. I should be able to wake you up at 2 a.m. and say, what's the latency between New York to San Francisco? 72. No. What's the latency to London? 72 milliseconds. Hong Kong, 270, right? 250, something like that. In fact, I was talking about this, and you'll see Gerald has in the newest, there's a Lua script that takes round trip time and calculates the speed of light because it's constant, whether it's in coax fiber or microwave. They're actually different because the refraction. And he calculates the distance. So you can even measure distance from packets. Who knew, right? But so this is 40 milliseconds New York to Dallas, about 40 milliseconds, and that's the bad of asking for one row at a time. Again, 3 days, never finished. This is the exact same query where you see exact same setup, 40 milliseconds, and you see, what do you see here? Huge packet trains, right? And I showed you that before by looking at my normal method, which has the byte to push bit, meaning from push bit to push bit, how many do you have? 450,000. Why? Because I know the backbone, and I knew my backbone could take this much raw throughput. So the question was, how fast do you need to replicate the database? Fast as I can. I know. But realistically, you're not the only application on the backbone. What's the minimum viable number? They gave me a number, I did the math, how many rows are you transferring? X number of rows. I said, okay, I can give you 500,000 per round trip. So what's the throughput? The throughput is 500,000, I'm rounding it off, per 40 milliseconds. 400,000 bytes per 40 milliseconds. That's the throughput. What was the throughput previously? 363 bytes per 40 milliseconds. That's several orders of magnitude. So we took a transaction that went from 3 days, never finished, to less than 3 minutes. Okay, simple math, right? So again, this is another proof point that this is a database in play. Make sense? Yep. So look for that, and what I'll do is, if I remember, if you don't see it, I'll post some connection strings of JDBC, ODBC, SQLNet, bulk copy, that you can give to the DBA and say, hey, do you know about a prefetch size? At the very least, ask them that. On a select query, you can increase the prefetch size, and then you have to increase the TCP window size correspondingly, right? Because remember, when you ask for more prefetch data, you're asking the application to use a bigger bucket to pull, to dump that water into your TCP. So then the next bottleneck is your TCP window size. Your TCP window size that you agree on, right, sender and receiver, has to be big enough to match the bucket size of the data, application data, okay? Because if the database is using a giant bucket and you're using a little bucket, you're going to incur round trip penalties because the TCP window size is going to be full, okay? Make sense? All right. 11:15 we started, so we go to 12:30. Oh, okay. All right. So now let's look at another interesting trace file. This is interesting because you sort of kind of have to know TCP to figure this out. I'm not bragging, but it took me about 30 seconds to find root cause. This problem has been going on for this customer for 2 weeks. So what is it that I did that said, there you go, that's the problem? Again, going back to Ron Burgundy, kind of a big deal around here. I'm not. And I'll prove to you why I'm not. Because I saw this before, right? I saw this before, that's why I knew it. If I didn't know it, it would have taken me a lot longer. Simple, right? This is why you're here, to gain experience. Again, I can't teach you packet analysis in one day, but I can teach you philosophical things about how to troubleshoot. So, 2018, and is it ICMP black hole? Maybe. Let's see. Nope, that's not it. Let me, failure to download, no, that's not it. More ICMP issues, yep. And that you see that anon there, thanks to Jasper in the back. That means I used Jasper's excellent trace wrangler to anonymize this packet. That's it, 11 packets. So if I give you 30 seconds, can you find root cause? I'll leave it there for a second. It's hard to do because it's my screen and it's hard to see, but so let me move this over just a little bit so you guys can see better. So clearly there's packet loss. You see the dupbacks. You see the retransmission. You see the reset. You see that at the last 3 packets there? Dupback, retransmission, reset. So that's the symptom, not the root cause. The symptom is there's retransmission, and then the connection resets itself. Okay. Again, I saw this pattern before, so I said, this is your root cause. And I even gave him the command on a router to overcome this issue. So let's see what it is. This is a trace file that we can spend the next 15 minutes on, and maybe we will. I like to, because I want to do step by step and methodically tell you how I, in 30 seconds, said this is root cause, this is what you need to type on a router to alleviate this problem. All right. So there's only 11 packets, so we can spend 10, 15 seconds at a time, or a minute at a time, and we'll still be in a good shape. So let's look at the transmission control. So the usual things, right? Yes, it's a SYN. Yes, it's window size. Yes, I have options here. Okay, so I have maximum segment size and options here, eating up to my MTU MSS, right? So my MS is going to be smaller because I have to accommodate these fields, right? If I happen to use them, right? So because obviously 1460, if nothing here, if I have a bunch of sacks here, then it's going to eat up the packet's size. Headers. The headers are going to grow bigger. Here, it's my SYNAC, and same thing, nothing exciting. Okay, nothing exciting is going on. All right. So the first thing we need to find out is, am I closer to 192.168 or am I closer to 10.10.10? As mundane as it is, it's important because the picture looks different, so you need to know where you're capturing. And clearly, by looking at the delta here, moment in time, big bang, boom, I see a packet. I immediately see, because it's only 1 millisecond, right? I see a SYNAC, and then I see ACK, that's 47 milliseconds away. So where am I capturing from? Yeah. Okay, here, right? Everybody agree? Right? Because let me just walk that through one more time. Big bang, I don't know where I am. All I see is this one packet, that's all I see. I got blinders on. I see packet. I immediately see 10.10. So I'm probably close to 10.10 because I saw packet going this way, and then boom, another packet came very, very quickly. And then sometime later, 192.168 answered. So the round trip is probably about 47, 50 milliseconds. File that away. And then the other side, 192.168 guy, took some time to send me this data. Okay. Remember, this is my SYN, SYNAC, ACK, right? And how is it that he sent me 23 milliseconds later a packet when the round trip time is 47 milliseconds? Anybody know? It's a trick question. You might be thinking that, right? Wait a minute. If the round trip is 47 milliseconds, how did this guy send me something in half that time? So this is kind of a play on Jasper's example of, can you get a retrans or dupe back? Can you get a dupe back in less than half round trip time? When acceleration? Steelhead for the win! No, it's actually simpler than that because remember you have to frame. So Jasper's example was, it can't be possible because in order to induce that retransmission or dupe back, saying you missed a packet, that those packets in flight have to go to the other side. Some packets went missing. He says, dupe back please, and it has to come back. So at a minimum, it's a round trip to detect there was a packet loss, right? Make sense? You send some packets, it got lost along the way, and it forced it to send dupe backs, and that's a full round trip. Here it's half because remember, when my ACK got sent to him, he's free to send. And it's not a round trip penalty, it's only half a round trip because my ACK received him and he started to send to me. Anyway, it's a trick question. So here's 1016, 1460, and 920. We know that he sent this. Did he send this like right away? No, because there's some delay here. I'm sorry, this one here, and so let's look at here and here, okay? So big packet, 1460, little trailing packet. Okay. Big packet, little packet, and who am I acknowledging here? Okay. So big packet, little packet, and he sent me, let me move this over here, an acknowledgement from the 10 sides because I sent. So who did I acknowledge here? My ACK number is 1017. What's my next expected sequence number? This guy. Okay, I'm just walking the packet trace file. All right, everybody okay with this so far? Okay, so let's get down to our problem child where 192.168 says, hey, I'm missing a packet here. Here's a dupe back for you. Here's a dupe back for you. So what caused these two dupe backs to show up? 192.168 is telling me I dropped a packet. I even know which packet it is because you look at his ACK number. Okay, after the handshake, things broke. After the handshake, things broke. How do I know that? Because his ACK number is still at 1. Okay? So which means, which packet got dropped? What's my sequence number there? for this packet? 1. So this is me, 10 dot, sending data to the 192 guy for the very first time. I know that for a fact because my sequence number is at 1, and my next expected sequence number is 1460 more. So this is the very first packet train that left the station. And the next packet train started from 1461 to 2381. So far, so good. And then I acknowledged, the stuff that he sent to me. And then all of a sudden, 192.168 says, hey, DUPAC, the first packet went missing. How do I know that? Because there was a trailing packet. This is the only reason why I got an immediate DUPAC. The first train, so this is actually a short train, right? This is if you're like in New York, it's the S train, right? Just between 42nd and Grand Central Terminal. There's this 2-train packet that left the station. First packet went missing. The second packet showed up. So the duplicate ACK says, train number 1 is missing. Train number 1 is missing, right? Make sense? Everybody with me? All right. So then the question is, I understand the first DUPAC because train number 2 showed up. So again, setting the stage here. Packet number 1 went missing. Packet number 2 showed up. I let you know that packet number 1 is missing. So how do you account for another DUPAC coming in? The third, which packet number? So the question, so let me rephrase the question and then give me that answer back one more time. So the question is, I can account for this DUPAC. Of course I'm going to see a DUPAC because there was train number 2, which is this guy, that showed up. I can account for that. Where did this guy come from? Speak up for me one more time. It came too fast. I'm capturing from 10 dot, right? And so this DUPAC came, millisecond apart, right? And we already said that it takes trailing packets to cause duplicate ACK behavior, right? How many packets did I send? So, moment in time. So forget everything that happened previous to this. I can even do Control T for time reference. I can reset the clock if I wanted to. Okay, but it's not important. I will. So this is Big Bang. I can account for these 2. I know they left the station. So the question stands, how many packets did I send? 3. Who says 3? It's right there, it's 3. Okay, but what is that third packet? Didn't I just say that guy has no data? It's naked ACK. You don't acknowledge an ACK. You don't. It's a naked ACK. In fact, when ACKs go missing, no one knows. When TCP ACKs go missing, no one cares. So I ask you again, why do I can account for this. This is caused by packet number 2. Why the hell did this guy show up when I only sent 2 packet train? Wait a minute, I just said I sent 3 packet. Is there something special about the third packet? And there is. Fin, which is perfectly legal. I sent you 2 bytes a day, 2 packets worth of data, whatever that 1460 plus 920 is, and then I want to close my session. Perfectly legal. I sent you what I need to send to you. I'm done. I'm giving you a fin. Fin requires an ACK. Why? Because you go to fin wait state, you ACK, and the other guy goes to close wait, and then you go to fin wait 2 state. This is a modified handshake. So fin requires an acknowledgement. So fin, that fin packet, even though it's a 0 packet, naked ACK, forced the other guy to send me an ACK, which happens to be a duplicate ACK, because we're still in a packet loss recovery mode. Sorry for those of you on YouTube. Send your bill for hearing loss to wireshark.org and not to me. All right, so we get that, okay? We understand that. And then here's a retransmission. Of course I'm going to retransmit. Took a while. Took a long time, actually, right? Why? Because this is not a fast retransmission, right? Is it a fast retransmission? Nope, because I didn't meet the threshold of triple duplicates. Okay, so I took some time, a long, long time actually, and sent the packet again, and the other guy says, "See ya, I'm out." Why didn't I retransmit this? Why did this guy just so rudely hang up on me? So it took a long time for me to send, and then I rudely hang up on the guy. Why is that? It's some time or some application, who knows, right? I mean, we don't know. So got tired of asking. But this is a complete black hole condition. But it's not a complete black hole solution, because the first packet made it. The SYN made it. The SYN-ACK came back. I sent 2 packets. The full one didn't make it. The second one did. So if this was an access list or a firewall, how can the small packet make it, but not the big one? So packet size related problem, and the important thing you said before you said it's a packet size related problem was? MTU. MTU. So guess what happened? There's an MTU smaller than 1460. I guarantee you. Because anything smaller made it. Everything small made it, the full size did not. And then when I tried to recover by sending it again, I didn't hear it back for 6 seconds, and I just said, I'm out of here. So why does that condition occur? Because of 2 things. One, there's a firewall somewhere that prevents all ICMPs. Unfortunately, ICMP type 3 code 4 is the mechanism that tells you to make it smaller, please. Okay? This is packet too large, fragmentation required. If you're a router guy, if you do show IP or show IP ICMP, you'll see how many ICMP types that you're sending out. And you'll see packet fragmentation required, could not send. This is how PathMTU discovery works. I have to set a do not fragment bit, which they all do. I have to say, don't fragment this, please, so that I force the router to send me. If you didn't have this do not fragment bit, I would have happily chopped it up myself and sent it to you as an IP fragment. But you don't want that, because not Cisco, but any router, most of us use Cisco routers, right? Come on. So routers are not very good at keeping data and holding it and slicing it, and so it takes you off that hardware accelerated switching path, right? So you want to avoid fragmentation. The other problem with fragmentation is that different versions of code will send the tail end first and the head end first. It changes. So firewalls have to accommodate seeing an IP fragment before you see the more offset bit coming in. In other words, some firewalls are happy to say, hey, I realize this is a fragment. I'll sit tight. I'll wait for the head end to show up. I'll put it together and do my check and then send it on its way. Okay? If the head end shows up first, more offset is there. It gives you the offset number, and then you know the firewall knows how to deal with it. Some firewalls don't deal with that if you send the ass end first, the back end first. okay? If the caboose shows up before the engine, some firewalls, So again, it's just in general not a good idea to fragment. And here, why did this router along the path somewhere not fragment here? That's the question. So I said, hey, is this many to one? Do you have a bunch of different clients doing the same thing? Yep, this is a nightly download or update of pricing book, or there's a bunch of point of systems, there's a bunch of clients, there's a lot of you and me doing this to you all the time. Clue number 2, boom. What happens is that every router in the world, ICMP protects itself by control plane protection. I will not send out infinite number of packet too large, fragmentation required. That's ICMP type 3 code 4. Okay? Because it's a way to DDoS the router. Every time I have to send an ICMP, I have to send it up to the CPU. I process switch that bad boy. Because the CPU has to get involved and calculate, hey, the next top MTU is 1310. So please, this is your original header. I'm just generating an ICMP that says the next top MTU is 1300. Please make it smaller. That's a CPU process. It's expensive. And if you send a bunch of those packets, CPU is so overwhelmed with trying to do that it can't do anything else, and you start dropping packets. So routers in general, control plane protection, they'll have a limit of how many control type 3, ICMP type 3 code 4 it'll send out. And the symptom is, for the most part it works, but sometimes, seemingly, it doesn't work. And the next night, it'll work. The next time, it won't work. It's all over the map. And all it takes is simultaneous request of this coming in for X number of people to get the ICMP type 3 code 4, make it smaller, and some that fall by the wayside. You never get the packet too large, fragmentation required, make it smaller, this is the MTU to make it smaller message, because the router says I need to protect myself and only the first X number of people get that in 1 second interval. So in 1 second, I may send 2, I may send 4, I may send 8. So there's actually a command that you can use, IP-ICMP rate limit unreachable DF, 100 milliseconds, 10 milliseconds, 50 milliseconds. Okay? So the lesson here is, this is a pretty interesting trace file, because you have to know that this duped back, but you had to have asked yourself, why do I see 2? I should only see 1, until you look further to find that fin. And that immediately clues you in to a whole bunch of information, right? That this is a black hole of large size, not a complete black hole. Okay? That retransmission timeout occurred as it should, because I don't have a triple duplicate to force the behavior. That there is a router, very, very likely a router, because sometimes it works, sometimes it doesn't. So let me show you what that ICMP message looks like, so you can see it. And remember I told you I saw this behavior before. This is the first time I saw it. And this was a pretty big deal, actually. And it went on for a long time until, we caught this in action. And there it is. So this is the ICMP message that says type 3 code 4. Here's the original header. This is the original conversation. And I'm letting you know the next top MTU is 1430. This is how path MTU discovery works. And as a host, when you receive ICMP type 3 code 4, what do? You update your routing table. You create a host-specific route entry with the next MTU size of 1430. This is how you know that when you continue the conversation, you need to make it smaller. Okay? So just because, remember, you could just accept it from faith that I said it, so it must be true, but always ask yourself, why? How does a future packet know to send it that? Because you create a host route. So if you look at the RFCs for ICMP type 3 code 4, you'll see path MTU discovery, you'll see that The host's job, the sender's job is to create a host-specific route with, and you can use netstat to see this, the gateway and the maximum MTU size. Okay? Is that pretty interesting? I mean, I thought it was interesting because it's only 11 packets, and here we are, we spent almost 20 minutes on 11 packet trace file. It goes back to what we always talk about, all the instructors. Know TCP. Know what a thin weight is. Know what the ramification of that is. Know what, you know, black holing of large size means. Know why triple duplicates matter. Know why SAC matters, right? You have to have an arsenal of experience that you built up over time to be able to solve these types of problems. Okay? And if you actually look at the, here, you can see how old this problem was, right? Because, oh, did I? Oh, there it is. So this happened years ago. It happened on February 2nd, 2004. That's 14 years ago. Was it that long? Jeez. Wow, I didn't think it was 2004. But this was a huge issue for us that caused people, teams of iOS developers, to try and figure out. Okay? And it had been, so this problem, not the 11 packet trace file, this one was, it impacted a lot of branches, and it was random, and I happened to walk by, and of course I was drawn to Wireshark, and I was like, what are you doing? That led me to this, which wasn't, not that it's hard to find, but it took longer than I thought because I had to rule out my usual suspect before I got to here. Now, that's 14 years ago. This other trace was from April of this year. It was in fact at Singapore Sharkfest when somebody brought it up to me and said, hey, I don't understand this trace file, can you see it? 14 years later, because I filed it away like a little squirrel, I saw this behavior and I said, oh, I know what this is, path MTU discovery. Do you have a lot of these clients? Yes. Does it go to a same server? Yes. Do you have a router with a GRE tunnel for IPsec? Yes. Case closed, boom, move on next. Okay? Questions? Experience matters. In packet analysis, more than anything else, experience matters. But knowledge matters. Because remember, just because you've been doing something for 20 years doesn't mean you've been doing it right for 20 years. So every old timer like me that says, I've been doing this for 20 years, I know what I'm doing. Yeah, you may not have been doing it right for 20 years. How about that? So always learn. Every session I go to, whether it's Jasper's or Christian's or anybody else, and Chris's, doesn't matter who I go to. When I go to somebody's session, I learn something new, a new way of doing something. So this is more about philosophy of packet analysis. You have to know it, you have to scroll it away, and you have to always ask why. Don't assume, don't go over it. If something bothers you, research it, get to that, nth degree, because there's no other way you're going to learn this behavior. Be a good packet analyst or protocol analyst without asking questions all the time. Any questions? Okay. I do have one packet trace to show, but I'm going to run out of time, so I'm not, but I'll just give you, actually let me stop the recording here because I didn't finish anonymizing this. So I'm going to stop the trace file here. So all you YouTubers, it's cliffhanger, unfortunately for you, because I'm going to stop the trace.